right, hello everyone. For those of you who don't know me, I am Miss Hu, your physics teacher. Now, in this video, I will be going through with you the examples in a textbook about forces in equilibrium. So if you have this textbook, all right, please open to page 21. We will be going through the diagrams in examples 1, 2, and 3. Now, I will not be going through the answers exactly as per the questions in the examples. Instead, in this video, we're going to be using the diagrams from the examples as a basis for our problem solving, and we will learn to solve the unknown values of forces. Okay, without further ado, let's begin. Yeah, and I put a meme here, I thought it was quite cute. Okay, so we have in here, in this slide, we have the diagram from example number 1. And in this example, we have an object, which is the lamp, suspended from the ceiling like this. So it's held in place with two different strings at different angles. We have string here with a tension in it labeled as T, and the value given is 8 Newton, 60 degrees from the horizontal. We also have another string over here. The tension in the string is P, and W is the weight. It's not written in the question, but this is actually 90 degrees to each other. Okay. So we are given T. We need to find the values of P and W. Okay, again, I'm not following the questions in the examples. We're going to look at how to solve the values of P and W, which are unknown. There are actually two methods which we can use to solve this, and I'll go through both. But before we go into that, let me just explain a little bit about concept of forces in equilibrium. Now, forces in equilibrium, as you should know by now, it means balanced forces where the net force is 0. Normally, if the forces are directly opposite to one another, right, it's easy to compare, because if the forces are directly opposite to each other, this force equals to this force, or if it's the other way, this force equals to this force. But when you have three forces acting at different directions, it's a bit harder to compare. So then how do we solve it? One method is to use the resolution of forces. If you do not know how to resolve forces, I suggest you learn that first, and you can watch the video, which I'm sharing right now in the link here. And you can first learn how to resolve forces, and then come back to this video to understand now how we use this method. So in this case, we will resolve the forces that are acting at an angle. Well, there's only one force, so we're going to resolve the value of T, 8 Newton, which is acting at 6 degrees, into Tx and Ty components. So I'm going to use, let's say, use blue. Okay, blue might not show up, so let's use yellow. Okay, if that's even worse, let me change color. Let's use green. So we have Tx, let me put this color, hopefully that's visible. So this would be our horizontal component, which is Tx, and this is our vertical component, which is Ty. Let me label that Tx and Ty. So we're going to now resolve Tx and Ty, and I'll just draw it outside here in the Jamboard so that it's a lot more visible and easier to determine the values of Tx and Ty. So we have T at 8 Newton over here, Tx, and oops, let me put it a little bit outside so that it's more visible. Tx and Ty acting at 60 degrees. Sorry, T is acting 60 degrees from the horizontal. So from here, to find the values of Tx and Ty, Tx, as you can see, is adjacent to the angle of 60 degrees. So which means that if you want to find Tx, you can use Tx over the hypotenuse of 8. Adjacent over hypotenuse is cos, so that's cos 60. So to find Tx, that would be 8 cos 60, which gives us 4 Newton. Ty, on the other hand, let's use this color. Ty is opposite to the 60-degree angle, so Ty over hypotenuse of 8. Opposite over hypotenuse is sine, so that gives us sine 60, which means to find Ty, it would be 8 sine 60, which is 6.93 Newton. So the purpose of resolving the force T into Tx and Ty is because now we can get the two forces that are directly opposite to one another. So you can see in this case, P is directly opposite to Tx. That means the value of P would be equal to Tx if it's in equilibrium, which means P is 4 Newton. W, on the other hand, is directly opposite to Ty, which means that the value of W can be compared to Ty, which means it is 6.93 Newton. And ta-da! There we go. Okay. In case you're wondering why I keep looking here, that's because the screen where I'm scribbling on is actually over here. That's why my eyes keep going there. Okay, so that's the first method. Second method is, I'm just going to copy and paste, guys. Okay, method 2, we will use the triangle of forces method. The triangle of forces method will require us to draw the triangle first. That means we take these 3 arrows and arrange them into a closed triangle. So what we can do, I'm going to do it like this. We're going to start with W first. So W weight line goes vertically down this way and label that as W. Next, at the tip of the weight arrow, we draw the next line. I'll draw P going to the right because there's no space to go up for T over here, right? So we're going to draw P this way. And T is going up diagonally left. And that's how we get a triangle that's a closed loop like this. Now, if you draw the triangle the other way, and I'll just show you the other triangle, which is weight this way, the tension force goes up, and P, this is also correct. But you must remember though, 60 is not inside, 60 is between T and the horizontal, which means this is 60 degrees. So either one is fine as long as you draw the correct triangle with the correct forces in the correct direction. Now, in my case, I'm going to use the triangle on the left to solve this. So because it is now a triangle that's closed, and this is a 90-degree, or rather right-angle triangle, I'll just use a different color so that's clearer. We can also use the trigonometric functions to solve this. So, for example, now if I want to solve P, P is the adjacent to 60 degrees. So again, P over hypotenuse T, which is 8. This is adjacent over hypotenuse. That gives us cos. So cos 60. Therefore, P is 8 cos 60. Whoops. Okay, that looks terrible. Let's rewrite that. Which gives us 4 Newton. And there you go. W, on the other hand, is opposite to the 60-degree angle. So opposite over hypotenuse of 8, that gives us sine. So that's sine 60. So W is 8 sine 60, and this gives us 6.93 Newton. And voila, there you go. So if you look at methods 1 and 2, you're going to get exactly the same values. Like, duh, you are supposed to get the same values. Just because you use slightly different methods doesn't mean you will get different answers. You're supposed to get the same answer. The difference between these two methods is how we start approaching the question. So in method 1, what we do is we resolve the force at an angle first. That means we resolve T into horizontal and vertical components, and then we compare those that are exact opposite directions. Method 2, on the other hand, starts off with a triangle of forces first, and we use the triangle, which is consisting of all 3 forces from the free body diagram, and we use that to solve the question. Of course, in both cases, because of the existence of this angle, there will be sine and cos involved. And that's why we find, looks like almost the same. Yep, they're almost the same, just that the approach is slightly different. Now, to solve the diagrams in examples 2 and 3, you can also pick either method. I'll show for both method 1, resolution of forces, as well as triangle of forces. Okay, so let's see, I'm just going to copy and paste the text. So in this case, before we can start solving this question, we do need to have the free body diagram, and we'll get the forces from the question. There's the weight, pulling it down. There's the normal reaction, which is 90 degrees to the surface, which I'll label as R. and friction, which goes against the direction of slide, which I'll label as FR. Now, to solve this question, this is very similar to what you've learned in resolution of forces. You'll find that FR and R, because these are 90 degrees to each other, we'll keep these two and instead we'll resolve W. So resolving W into Wx and Wy, that means Wx is parallel to the surface of the incline and Wy is perpendicular to Wx. Now 40 degrees, let's look closely how to get the angle. If this is 40 degrees, this is 90, this is 50. So I'll just label that for clarity. If this is 40, this is 40, this is 90, sorry, this is 50. What am I saying? Got distracted. 50 because parallel angles, so 50, 90, therefore this is 40 degrees. So I'll just draw the triangle outside here for clarity. So this is W, this is Wx, and this is Wy. And angles here, 90 and 40. I'm just going to keep 40. We don't have to write both. Now, in this case, though, because Wx is opposite to W, that means Wx over W, which is the hypotenuse. And I think the value is given. Let me just write that down. W is given as 50 Newton. So Wx over 50 is now opposite over hypotenuse. That's sine. So that's sine 40. Bringing that up, Wx equals to 50 sine 40. And 50 sine 40 is 32.14. As you can see, Wx is directly opposite to friction. So if we're looking for the value of friction, because this is an equilibrium, friction is equal to Wx, which is 32.14 Newton. Let's use red. So Wy, on the other hand, is adjacent. So again, adjacent over hypotenuse, which is 50, that we cos. So that's cos 40. So to find Wy, it is 50 cos 40, which gives us 38.30 Newton. As you can see, Wy is directly opposite to R, which means that R is equal to W, and that value is 38.30 Newton. So that's how you solve this question using the resolution of forces. Now, I have been asked before, is it possible that we maintain W as the vertical line down and we resolve FR and R into the horizontal and vertical components respectively? It's possible, yes, but in this case, I'm opting to use this method because we have learned this method in topic 1.2. So since we've already learned it before, let's just use what we have learned. Now, let's attempt this using the triangle of forces method. So I'm just going to do this. I'm going to copy the title, all right. Okay, so to solve this using triangle of forces, we still need to have the free body diagram first. So this is the weight, normal reaction, and friction. Whoops, let's put it closer to the surface. Friction. Okay, in this case, okay, weight line is here. Whoops, W, which is 50 Newton. I'm just going to add that in, 50. And, whoops, yeah, R is here and FR is here. So do we get the closed loop? Yes, we do. Tap, tap, tap. So this is 9 degrees. And you also need to get this angle anyway. So you can see that 40 is between the friction and the horizontal, which means you can imagine it this way. If this is 40, dotted line here. Okay, so this would be 40, which means this is 50 because triangle this way. That means this is 40 degrees. Whoops. So to solve this, let's remove this so that it doesn't interfere with our solution. Okay, we're going to focus on the 40-degree angle because it's easier to just use back the same number that's in the question. So to solve R is adjacent to 40, adjacent over hypotenuse, which is 50, is cos. So that's cos 40 degrees, which means R is 50 cos 40, which is 38.30 Newton. FR, friction, on the other hand, is opposite. So friction over 50, opposite of hypotenuse is sine. So friction is 50 sine 40, which is 32.14 Newton. That's how solve it. So same, right? Because I solve R later. So 38.3 for R and friction is 32.14. And now we can also use the same methods to solve this. All right, so for example 3, okay, we can also solve this using resolution of forces or triangle of forces. So you can see over here from the diagram, they've given us the 3 forces. We've got the weight line going down and 2 tension forces acting here. Now in this case, the 2 tension forces are equal because for one, they're both labeled T, and secondly, which is the more practical reason, they're both acting at equal angles from the horizontal. So to resolve, if we want to resolve the forces in this diagram, we need to resolve these 2 forces which are acting at an angle. That means both T's have to be resolved into horizontal and vertical components. I'm going to use different colors for clarity. The left triangle here is blue. I'm just using a thicker marker so that it's clearer. This will be our Tx and Ty. And the right triangle, we'll use green. Okay, and this will be our Tx and Ty. Now, because the values of T are equal, this means that both Tx's will be equal and both Ty's will be equal. Let's look at Tx first. Tx on both sides are equal, but they're acting in opposite directions, which means they're going to cancel each other out. So we don't have to calculate Tx because no point. Tx equals Tx, and then you're like, oh, okay, there's nothing to count. They're just going to be nullified, going to go down to 0. So let's focus on Ty. Okay, now from the question, it's given here that W is 12 newtons. I'll just write that in. And to solve this, we can see that both Ty's are acting upwards opposite to W. So 2Ty, whoops, let's use a darker pen because that's not very visible. 2Ty equals to W. And we know that W is 12. So that means 2Ty equals 12. That means each Ty is 6 Newton. Now this is of course not the answer. We're still looking for T, but now we know what Ty is. So Ty, as you can see, is opposite to the 35-degree angle. T is the hypotenuse which we are looking for. So 6 over T equals to, opposite of hypotenuse is sine 35. So to find T, it would be 6 over sine 35, which gives us 10.46 Newton. And that's how we can solve the value of T using resolution of forces. We can also solve this using triangle of forces. Okay. So what we need to do, of course, first is we need to draw out a triangle of forces. I'm going to draw a big one here for clarity. So the weight we know is 12 Newton. Let me just add that in. Okay. Weight line going down. And then tension at an angle and tension at an angle. Now, the labeling of the angle. So you got to be careful. 35 degrees is between tension and the horizontal. So it's not on the inside, it's on this side, on the outside. So it means it's 35 over here. Whoops, that's not straight. Let's make it straight. So this is 35. And likewise over here, okay, that's not straight. This is 35 degrees. And for this angle, the Z rule, this would be 35. So this 35, 90 minus 35, this gives us 55. And over here, if we have this triangle, right angle triangle here, 35, this would give us 55. And that's how we get this triangle of forces. Now, to solve the value of T from the triangle of forces, there are two methods. So if you know at maths, you can use the sine rule. If you don't, you can actually still use trigonometry, which is sine, cos, tangent. I'll show you both. For this explanation, I'm just going to copy off this diagram and put it on the next slide, which is blank. And let's use the sine rule first for those who know at maths. So what is the sine rule? The sine rule, if you recall, it's A over sine A equals B over sine B equals C over sine C, which means the length of the side over the sine of the opposite angle is equal to the ratios of all the others as well, which is the length of the side to the sine of opposite angle and so on. So based on this triangle, let's take A first. This is T over the opposite angle is 55, so that's sine 55. W, the opposite angle is 35 times 2, which is 70. And the other T over 55. So you don't have to solve both because, it's exactly equal, right? So we'll just take one side. And we now know, we already know that W is 12. So this gives us T over sine 55 equals 12 over sine 70. And from here, when we solve it, it's 12 over sine 70 times sine 55. Work it out, you will get 10.46 Newton. And that's how you can solve it using the sine rule. Let me put that in here. This is the sine rule. But what if you didn't learn the sine rule and you're not sure how to use it? Can we still solve it? Yes, we can. So here's how you can solve it, and I'll put this on the next slide again. Another method is to use trigonometry, which is what I've been doing all this while, right? Okay, but how? So because the tension values are equal, it means that if you were to divide this triangle into two, you'll get two congruent triangles. As you can see, the top and bottom triangle, right, got 55, 35, and 90, both equal because the tensions are all equal. So when you do this, you divide into two, it means that this weight line will also be divided into two exactly. Now, this only works when you have equal tensions. If the tensions are not equal, like if this is T1 and T2 and different angles, you won't be able to use this method. However, because conveniently the tensions are the same and you got two congruent triangles, that's why we can use this method of dividing this into two. So I'm just going to draw it out for clarity. So we have a triangle like this. And now the horizontal line is not an actual force. We're going to put that as a dotted line. So we've got T over here, we've got 35 degrees. And now, because the weight line has been divided into two, this line is equivalent to W over 2. W is 12, right? So 12 over 2, that gives us 6 Newton. So to solve T, you can see that T over here is the hypotenuse, and we have 6, which is the opposite to 35. So opposite over hypotenuse, that's sine. So T is 6 over sine 35, which if you work it out, you will get 10.46 Newton. So in this video, we have covered the different ways of solving different problems involving forces in equilibrium. So you can use resolution of forces, which means you use the approach of resolving the force at an angle first to its horizontal and vertical components. Or you can begin by drawing the triangle of forces and use a triangle to solve the values of the unknown forces. And even within a triangle of forces, you can use the sine rule or you can use trigonometry. Now, remember, you can only use this method if it's a right angle triangle. If the triangle is not a right angle, like in this case, you can't use sine, cos, tangent. Instead, you can use the sine rule or find a way to create right angle triangles. Now, there is no one way that's better than another. You can look at the situation and find which method works for you. If you find that the resolution of forces make more sense, go ahead and use that. If you find that the triangle of forces makes more sense, use that instead. And you don't have to limit yourself to, oh, I only can use triangle of forces, or I can only use resolution of forces. If you find one method makes more sense than another, then stick to that for all. But if you understand both and you find that, okay, this situation, it's easier to use this method, then feel free to use that method. It's more important. I mean, it's the more important thing is that you get the correct answer and not so much that, oh, use the easier method. Okay, sometimes you might need to use a little bit more effort, but as long as you get the correct answer without confusing yourself, that's fine. So I hope you have found this video helpful and educational. Don't forget to click like and subscribe for more lessons just like these.